In this concept, now we're going to try to improve upon the previous setting. While having a trusted aggregator is certainly a nice feature, the problem is that in some cases there won't be a natural person to actually fill this role. And it can be a bit inconvenient and maybe suboptimal to still have to trust someone to actually see the raw version of the gradients that each individual data owner is generating. So what we'd like to do instead is we'd like to leverage a form of cryptography called additive secret sharing to make it so that we can actually aggregate these gradients in an encrypted state. The idea here being that we can perform the aggregation while the gradients are still encrypted, thus no individual person will actually see what those gradients are. In particular, in order to do this, we first need to introduce a new form of cryptography called additive secret sharing. This additive secret sharing is just a simple technique that allows multiple different individuals to add numbers together without finding out what anyone else's original number was. So if we have two individuals, Alice and Bob, they can each compute the sum of a number that each of them own without actually revealing what their inputs are to the other person. To explain this, I want us to consider less from an encryption standpoint and more from a shared ownership or shared governance of a number kind of standpoint. So let's consider this variable x. We'll say x equals 5. And then we're going to split this x into two shares, okay? So we're going to have Bob's share, which is a 2, and we're going to have Alice's share, which is a 3, and 2 plus 3 equals 5, which is how we restore it. And you'll notice that we can sort of decrypt x by simply adding these two shares together. And the most important thing to take away from this is to notice that Bob, by just looking at his own share, which is the number 2, has no idea what x actually is, because this share doesn't actually describe any information about x. And we see the same for Alex's share, 3. But the truly fascinating part about this is that while Bob and Alice, in this shared state, can actually perform computation or arithmetic on this number that is split between them. So if we see here, let's say that Bob and Alice wanted to multiply this hidden number by 2. If Bob multiplies his share by 2, 2 times 2 is 4, and Alice multiplies her share by 2, 3 times 2 is 6, then we look at the result, we'll see that when we decrypt it, it actually decrypts to a 10 instead of a 5. So as you can see, this technique seems to work quite well, and it's extremely efficient. There's not a lot of extra computation that's required, and we can even use it for the use case we care about here of adding two different numbers together. So let's say we have the number 5, which is Bob's number. He splits it into two shares and sends one to Alice. So Bob has a share, which is a 2, and Alice has a share, which is a 3, same as before. But let's say we have another number, an encrypted 7 for the variable y. Bob's share is a 5, and Alice's share is a 2. So again, 5 plus 2 is 7. And what we see here is that if Bob adds his two shares together, his x share and his y share, and Alice adds her shares together, her x share and y share, then Bob and Alice have just created a new shared number, which will decrypt to equal 12. So we just added 5 plus 7 equals 12. And the nice thing here is that this is a really simple protocol for being able to do encrypted addition such that neither Bob nor Alice see any of the inputs. They only see the inputs that they bring to the table. And that's a really nice property. However, the protocol is still broken in one important way, which we'll fix in the next video.